Hello everybody and welcome to the Module 12, is this 12? Yes, Module 12 video for Introduction to Logic. In this video, we will be learning about quantifiers and quantificational schemata. So, if you were paying attention in the last chapter on the method of existential conditionals, you might have caught that I didn't really fuss too much over the translation between Boolean schemata and English. And the reason why is that Boolean schemata are kind of an intermediary between truth functional schemata and quantificational schemata. And what that means is, or for us, what that means is that these sort of quantificational schemata that we're going to be looking at today, all of them can be translated back into Boolean schemata. So despite the fact that I'm introducing a new type of schemata, you already know the validity test for it. But the advantage of quantifiers is going to become really clear. The advantage is that Boolean schemata are horrendous to translate to and from English. It's very hard to look at a Boolean schemata and understand what it says in English. It's very hard to look at an English sentence and have a nice intuition about what Boolean schemata would correspond to that sentence. So don't panic just yet because we're getting a new type of schemata. All this is kind of a more developed, readable sort of Boolean schemata in this chapter. Once we move on to like chapter 14 and 15, there will be certain types of quantificational schemata that we will not be able to translate back into Boolean schemata. But for right now, we're not going to look at those. And so in this chapter, we'll be doing mainly three things. So the first thing is I'm going to explain to you what our quantifiers are, what they mean, right? And then the bulk of the chapter will just consist in translation. I'm going to tell you how to, given certain sorts of English sentences, produce quantificational schemata that correspond to those sentences. I'm also going to teach you how to transform quantificational schemata into Boolean schemata so that you can apply the method of existential conditionals. And finally, we are going to look at the semantics. And semantics just means like meaning or interpretation of quantificational schemata using a technique known as expansion. So how this chapter is going to go is there's not a whole lot of new complex stuff that you need to learn how to do, per se. There's a lot of conceptual stuff that will be very important for chapters 13, 14, and 15. And if you want to actually know like how to do something useful with the method of existential conditionals, teach you how to transform these quantificational schemata into Boolean schemata so you can do that. But this isn't there. There are a few rules, though I almost hesitate to call them rules because once you understand how to read the symbols, they'll be really obvious. But it's only like 2 or 3. It's nothing very scary. So, pay attention to the translations mainly, and hopefully this won't be that bad. So a good place to start when introducing quantificational schemata would be introducing quantifiers. And there are exactly 2 quantifiers in our logical system. The first one is known as the universal quantifier, and we represent that with an upside down A, and then followed by a variable here, which I'll get to in a second. And if we were to read this, these will always occur at the beginning of some schema or significant part of a schema. And when we see this upside down A followed by an X, It doesn't have to be an X, by the way. We could have a Y or any lowercase letter. We would read this as all X are, right? Or another equivalent way of reading it would be every X is such, such that, right? You'll see how this works once we actually get into fully developed quantificational schemata. The other quantifier in our language, you've already seen this, although you haven't always called it a quantifier, is the existential quantifier, which we represent with a backwards E followed by a lowercase x or y or z or a or b or whatever. And the, I guess, most logic-y way to translate that would be there exists an X such that, and then some other stuff that will follow the quantifier. So these are really the only new ingredients in our quantificational schemata. And whereas in Boolean schemata, we would abbreviate away the variables, here, we're not doing that. We'll always leave in the variables. And so a quantificational schemata is going to look like, just to give you a really simple example of one, something like this. And what this first example, example A, says is that, it says that every X is such that if it is an F, then it is a G. I will go through a bunch of the more ordinary examples of these shortly, but this says the same thing as our type A sentence from term logic. So what this says is all F's are G's. Right. So let's look at the other parts of this schemata to see what's different. So we have a quantifier, right, which I just introduced, and which will always come at the beginning of some schema or some part of a schema, right? So there are kind of two things to note about quantifiers. Quantifiers have two, I don't know what to call it, properties, features, characteristics that were absent in our previous schemata. So the two things to note about quantifiers, the first thing, anyway, is one, quantifiers have a scope. And the scope of a quantifier is indicated by the parentheses that follow it. So in example A, the scope of this universal quantifier is everything inside of the parentheses. This isn't terribly important right now, but starting in the next chapter, this becomes important to know, right? So the scope is just if the quantifier occurs next to some parentheses, then the scope is indicated by the parentheses. We could also have quantificational schemata that just govern one thing, and like we could have this is a legitimate quantificational schemata, and so the scope of this universal quantifier here would just be this, right? This is kind of a shorthand for that. just to cut down on parentheses, we won't always write them if the quantifier only governs one of these things, right? And the second thing to know about quantificational schemata and quantifiers is that quantifiers bind variables. And so what that means is we would say in example A that the universal quantifier binds the variable x, right? So if that x occurs inside the scope of a quantifier, right, that we'd say that this x is bound by the universal quantifier and this x is bound by the universal quantifier. And what I'm about to do is legitimate, but a little strange. We shouldn't do this because it's unclear, but it's not technically wrong, is if we wanted to have, hx here. So because the scope of the quantifier only extends to the end of the parentheses, the x here isn't bound by this quantifier, because quantifiers can only bind variables that are inside their scope, right? Let me just erase. Okay. So those are important things to know, but they're not terribly important right this second. So I would write that down and make sure you understand what the scope is and understand what binding is. So I'm going to just go through the other parts of this quantificational schemata. And so the first thing that I'm going to look at, the next thing I'm going to look at is this fx right here. So before we would have called this capital F a term. And so now we're going to call F a predicate. Right? It's just a notational difference between term logic and quantificational logic. It doesn't change anything, right? So the next ingredient of a quantificational schema, and I've already been sort of mentioning this, are these little lowercase x's, right? And the x's are variables. And even if we have like something that's not bound by a quantifier, like, I don't know, HA, right? This A here would also be a variable. It doesn't have to be bound by a quantifier to count as a variable. So the x's, oh, the colors are wrong here. I'm going to back up and erase. The x's here, one second. Sorry, I didn't plan this out as well as I thought I did. Okay. So the x's here, right, we will say are bound variables. Because there's this quantifier that binds them. This A here, we will say, is a free variable. And it's free because there's no quantifier with an A right next to it to bind it, right? Again, this isn't very complicated. It's just something that you should, like, I would write down these definitions, right? And just some more examples of scope, bound variables, or whatever. So consider the schema. Okay, so the scope of this universal quantifier is everything in the parentheses, right? So that's the scope. And this x right here, because there's an x next to the quantifier, is a bound variable. But this a over here, since there's no quantifier to bind it, is a free variable. And I'm mainly saying this for your reference when in the next chapter you're like, what's a free variable? I can be like, go watch the last video. Okay? And so, oh, by the way, if we have, I forgot I added this when I updated the chapter. If we have a sentence like Donald Trump is orange, this doesn't have a quantifier in it in English. It's just the sentence Donald Trump is orange. It doesn't tell us like every Donald Trump is orange or some Donald Trumps are orange or there exists a Donald Trump that's orange. It just says Donald Trump is orange. And so if we wanted to translate this, we would use a capital O for the predicate OX, X is orange. And this is just the way that we do translation keys in quantificational logic. And then we would use a lowercase t, that looks like an F, whereas T is Donald Trump. Okay. And here, again, this T is a free variable, as there are no quantifiers to bind it. Okay? So what I'm going to do now is I'm going to give you the quantificational schemata that correspond to our 4 basic term logic forms. So if we use the key px for x is a pi, dx for x is delicious, what's the other one? Okay, then this is how we would translate these sentences into quantificational logic. So first, I'm just going to write A for a type A sentence from term logic. And the sentence is all pies are delicious. And that would go to and so what this says is, I'm just going to read it into English, is that for every x, if x is a pie, then x is delicious, right? And that's how we have to represent a sentence like this. If we wrote the sentence, what this one says is that for every x, x is a pie and x is delicious. So this one down here isn't saying that all pies are delicious. It's saying that everything is a pie and delicious. So what this is saying is that everything that exists is a delicious pie, which means something quite different from all pies are delicious, right? So that's the type A sentence. So if we have a type E sentence, such as no pies are delicious, we would write that like so. And the So if we read this out in the technical logicese way of reading it, we would say for every x, if x is a pie, then x is not delicious. And again, if we wrote instead this, right, what this would say, this schema, is that for every x, x is a pie and x is not delicious. So what that says is that literally everything that exists is a pie and not delicious. So everything that exists is a non-delicious pie. And again, that says something very different from no pies are delicious, right? The next type, our term logic sentence type I, some pies are delicious. And that goes to this. Right? So what this says is there exists some x such that x is a pie and x is delicious. And one really important thing to note, since for some reason, and I honestly don't understand why, note the difference between this and this, type A and type I sentences. So to say that all pies are delicious, we use a conditional arrow. But to say that some pies are delicious, we use conjunction. You will never, theoretically, it could come up, but for reasons that I will explain more clearly in the next module, you should never, ever translate, ever in this class, because it says something that's really weird, that I can't really get into until we learn the rules of passage. But what it says is it's something that you would never really want to say. You'll see in the next module. So you should never, ever have an existential quantifier where the main operator inside of the parentheses is a conditional arrow. So something like this, just nope. And you should especially not ever, if you want to say that some pies are delicious, think of a conditional arrow. What you want is a conjunction dot. I will explain why that's the case in the next chapter. But just pay attention to that. I would commit all of these forms to memory. And then our last term logic sentence type, type O, would be some pies are not delicious. And that's just this. Again, just reading that into strict logic-ese, there exists an x such that x is a pie and x is not delicious, right? So again, pay attention to the difference between the ways in which we translate type A and E sentences as opposed to type I and O sentences. Honestly, no matter how many times I say it, people still want to translate existential quantifiers with a conjunction arrow in the middle, but just don't, please. Please heed my words. Okay. So these four forms, these term logic forms, are kind of the basic building blocks for translating different types of quantificational schemata. And again, I implore you to just commit these to memory and make like flashcards with on one side, all pies are delicious, and then this on the other side, right? And you'll be happy that you did. There aren't exactly precise rules for translating between English and quantificational schemata and vice versa. So the only way to kind of develop the ability to do this is to look at enough examples that you can kind of start to see how the simple ones translate. For very complicated ones, I mean, philosophers argue about this all the time, right? Context is really important, and it's not always abundantly clear, but for everything that I will give you on a test, there's a pretty obvious, more or less correct translation. So, again, these correspond to our sentence forms from term logic. This is just another way of writing them into quantificational schemata. But I told you at the end of the term logic video that we would be coming up with a way of representing sentences that can't be expressed in term logic. So if we take our translation key here, what would I do? And we move it down. And then we add a third term, UX, which is going to stand for X is underbaked. And again, these are examples from the textbook if you want to follow along. So we can represent sentences in quantificational schemata that we could not represent in our term logic sentence forms. So if we have the sentence, all pies that are not underbaked are delicious. We would translate that into quantificational schemata, or into a quantificational schema like so. Right? Again, reading this in the formal logic keys, we would read it for every x, or every x is such that if x is a pie and x is not underbaked, then x is delicious, right? And the reason why we have to have a conjunction in the antecedent here is if we had if we had alternation instead, I guess whatever. Right, so if we have this, what this says is for every x, or every x is such that if it's a pie or it's not underbaked, then it's delicious. And so what this says is that all pies, what this says is that everything that's a pie and everything that's underbaked is delicious. I think. Anyway, I hope that's right. Okay, so that's one example. Just another example of a more complicated schema that we couldn't really do in term logic, but we can represent now. Let me add SX for X is a pastry. Pastra, no, pastry. Okay, so if we have the sentence, I'm going to write if something is a pie or a pastry, then it is delicious. This sentence says the same thing as the sentence, all pies and pastries are delicious. But this brings out that it's an or more. So how we would write this is like so. Again, I'm going to give this the really logic-y reading. So there exists an x such that if x is a pie or x is a pastry, then it is delicious. Then x is delicious, right? And again, this says the same thing as all pies and pastries are delicious. I apologize that there's a way of saying this sentence that makes it seem like it has a different logical operator, but that's just how it goes. I didn't make up predicate logic. Okay. And then if we wanted to say, just as one more example, some things are pastries or pies, we would translate that into logic like this. Right? And what this says is that there exists some x such that x is a pastry, or x is a pie, or x is a pastry. And this is because the distributivity of the existential quantifier from Boolean schemata still is a thing. So this is equivalent to which technically there exists some x such that x is a pie, or there exists some x such that x is a pastry. Okay. Not that bad. Also, I should just show you an example. It's okay to, we can have, I'm just going to write a schema and not try to come up with a translation for it. Okay, actually, so let's let fx for x is a frog, and then gx for x is green. And so this is a perfectly legitimate schema in quantificational, it's a perfectly legitimate quantificational schemata. And the main operator of this is a conditional. So if I ask you what type or what kind of sentence is this, you would say it's a conditional. You know, we could also have a conjunction here. If we wanted a dot, we could have an alternation. We could have a biconditional, right? So for quantificational schemata, I guess you could say that if we take any truth functional schema and we replace the P, Q, and R or whatever with quantificational schemata, we still get a quantificational schemata. It's just this is, truth functions of quantificational schemata or whatever. Just to show you that this is possible. And so if we would translate this as, with the conditional arrow, if all frogs are green, that's what that says, then some frogs are green. I'll just write that out. Or, I mean, another way of translating this would be, if all frogs are green, then there are green frogs. Anyway, so that's acceptable. And so all of the predicates that we've been looking at so far are known as monadic. Monadic? I don't know how to pronounce that. Monadic predicates. And those are things like AX or BY or FZ or PR or whatever. So a monadic predicate is going to have one term letter, I guess, and one variable. So we won't be looking at polyadic predicates until, for another chapter or two. But just to show you what monadic predicates are contrasted with, we also have, or will have, polyadic predicates. Such as fxy or gabc or lba, right? And the difference between monadic and polyadic predicates, obviously, is that polyadic predicates, though they only have one term letter, can have multiple variables after them. And so just to give you an example of how we would read something like this, what's a good example? So if we take fxy as meaning x is friends with y, then, and we, I don't know, I was going to use Trumpingham, but does Trump have any friends? Okay, let's take O for Obama and B for Biden. And if we wanted to say Obama is friends with Biden, we would say F-O-B. And the order matters here. But anyway, so that's just what a polyadic predicate is. So when I tell you things about monadic predicates, you can be like, oh, those things that aren't like polyadic predicates, the things that only have one variable. And so here's a really cool fact. Every monadic quantificational schemata has an equivalent Boolean statement schema. Or schema. I always screw up the plurality of this. I apologize for that. I don't know why. It's just those words. Anyway. Okay. And what that means is that this class kind of goes in a weird order because the validity test for monadic quantificational schemata. Oh, and a monadic quantificational schema is just a quantificational schema that doesn't have any polyadic predicates or relational predicates or two-place predicates or whatever. They get called different things in different books. So the method of existential conditionals is your validity test for monadic quantificational schemata. You won't really be able to apply it to all monadic quantificational schemata until the next chapter, where we learn some rules to move the quantifiers around in a way that'll make them amenable to the method of existential conditionals. But so there are 3 rules, and these are important, that allow you to always turn universal quantifiers into existential quantifiers. So the first one, these don't have, I'll do that. These don't have names again. I apologize, I guess, it's Quine's fault they don't have names. So these are just equivalency rules. The first one is this. And the dots are just something that it is inside the scope of the quantifier. So what this says is that if we have a negation before a universal quantifier, which we would read as not all x are such that, that is equivalent to, we can rewrite this as this, which says there exists an x that is not such that, or something like that, or there exists an x that is not whatever, right? And that should make sense, right? If if it's not the case that every number is odd, then there have to exist some numbers that are not odd, right? So the second one of these is this. I just saw a typo in the textbook, damn it. Okay. And so what this one says is that if we have every x is such that it's not ... that's equivalent to there doesn't exist an x ... right? So if we say everything that exists is not a round square, says the same thing as if we were to say it's not the case that there exist round squares. I'm just translating each side of these as I go along. If you say them out like I'm doing, they're really obvious. It's just kind of what these things mean in English. Okay. And then the third one is x, blah, blah, blah. Right. And so what this says is that if we have, every x is ... that says the same thing as there doesn't exist an x, there doesn't exist an x that is not ... right? So if I say that, every even integer is divisible by 2 without remainder, that says the same thing as if I were to say there doesn't exist an even integer that is not divisible by 2 without remainder. Right? And so if you want a maybe simple way of kind of, I guess I didn't write this in the book, but we could have, this is an equivalency that holds to if we have, you just don't need it directly to do the method of existential conditionals. If we have that's just equivalent to that. So this says if not every x is not blah, 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 that says the same thing as there exists some x that is blah, blah, blah. Right? I'm not going to go through that. So an easy kind of, you could remember those as rules, or you could remember, here. So I guess another way of thinking about this is that how these work is if you want to transform a universal quantifier with like a negation sign in front of it into an existential quantifier, what you do is you move the negation sign to the other side of the quantifier and then switch the type of the quantifier. So all of this is like a shorthand that encompasses all of these rules, basically. So this is equivalent to right. So if you have that's equivalent to right. And even if we have something like this, so this is equivalent to, remember, double negations cancel out. What that also means is that we can double negate anything that we want whenever we choose. If we had not. So this right here is equivalent to, and if we just flip one of the negation signs to the other side and change the quantifier from a universal to an existential, we get, or oops. Right. So just to give you an example of what this looks like, I'm going to give you an argument in English, translate it into quantificational schemata, and then show you how you'd set it up for the method of existential conditionals. And again, this is in the book on, I don't have the page, but it's in the book. So premise 1, all pies are either delicious or underbaked. Premise 2, no pies are underbaked. Then our conclusion is all pies are delicious. So put in the obvious letters. The first premise in quantificational schemata looks like right. Second premise. No pies are underbaked, just like this. And then the conclusion is okay. I think that's right. Anyway, pretty sure it is. So we have these 3 universal quantifiers out here. So what we're going to do to convert these into Boolean statement schemata is we use these equivalency laws or rules here to transform the universal quantifiers into existential quantifiers. Then we tear out the x's, and it'll look like a Boolean statement schema, because it'll be a Boolean statement schema. Okay? So for 1, how we do that is, and I'm just going to rip out the x's all at once. Premise 2. The conclusion. Right. And so this is more or less set up for the method of existential conditionals, but I'm going to solve a mystery for you guys as to why so many of the examples of the method of existential conditionals ones looked the same. And that's because I stole all of those from another logic textbook in quantificational schemata and then converted them. So if you remember, we have this. So we could just do the method of existential conditionals here, but something that'll make your lives a little easier is, if you remember our good old rule for eliminating negated conditionals, this. So what we can do here is, for each of these, we can apply this rule. So just to clean things up and make the truth value analysis easier. So and this is going to be I should probably use brackets, but oh well. Then 2 is then the conclusion is this. Okay. And I mean, while we're at it, so let's just De Morgan's this to simplify it even further. If we do that, that gives us oops. Sorry, 1 second. Failing here. And again, just to clean some stuff up, this is, oh, that's ugly. Scoot those over a little bit. Okay. And so this is all ready for our method of existential conditionals. And I'm just going to do this. I didn't do it in the book, but it doesn't take very long. So, or just to convert. So this is negated here, so we got to put it to not P. Same for the other ones. Q, R, and then okay, I skipped a few steps there, but I hope I'm entitled to do that now and it didn't throw anybody off too much. And if we plug our stuff back in, we get, so R is, it's going to be E. So that's, I really shouldn't have picked a U. U's a bad letter to pick. Okay, and then what we do now is we have to just make some space. We have to factor out this existential quantifier here, right, to make the consequent of our conditional a Boolean existence schema, or a single Boolean existence schema, and that gives us, I'm just going to do it on here, so ta-da! And so then we just test, which we can do using fell swoop, whether or not P and not D implies, oh wait, should that, yeah, that U should be negated, right? Yeah. So fell swoop, P true, D false. So it's true, true. Oh wait, should that be negated? Yeah. Wait, did I screw something up? Oh yeah, okay. So, yeah, I knew that I did something wrong. See, I make mistakes too. To explain to you what I did wrong, because maybe this will be useful, is so I tried to apply this equivalency rule to this premise to get this right, and not keeping track that this u here was negated. I didn't remember to, was already negated. I didn't remember to double negate it here. And so I screwed up, and this should actually be this. And that means that this should be like this, because I was like, I made this example to be valid, and I checked it 3 times when I taught the class last time. Right. And it wasn't going to come out valid unless I did that. So, see, I told you that I make these mistakes, and that's why you don't lose too many points for them. If you can do everything except keep track of negation signs in the class, you're doing pretty well. Okay, so truth value analysis. So we drop the. I assume that you have all done enough of these now. Oh wait, oops, I screwed that up too because I was thinking about why it wasn't going to come out valid. So this reduces to not u or u. Sorry, those are really ugly u's, which is true. Okay, and that's how you work through an example kind of from English to quantificational schemata to Boolean schemata to prettier Boolean schemata and then method of existential conditionals, right? It's not that bad, really. If you can do the method of existential conditionals, you should be able to do this. Okay. And in the next part of this chapter, I'm just going to explain the semantics and teach you something known as quantifier expansions. Be back with that in just a moment. Okay, so second part of this module is the semantics for quantificational schemata. Okay, so semantics is, in logic at least, the name that we give to the study of the meaning or interpretation of some sort of logical symbol that we have, right? It's contrasted with syntax, where syntax is concerned with the legitimate combinations of symbols, something like that. Anyway, so we had semantics up until this point in the class. I just didn't say that word, I believe. I might have, but I don't think I did. And so the semantics for truth functional schemata, stuff like if P then Q or R, if and only if S, right? Something like that, is given by the truth tables. And that means is that if you understand how to read in the truth tables, if you know what the upside down T and the right side up T stand for there, then you understand pretty much everything that you need to or could possibly want to know about our truth functional schemata. Unfortunately, we don't get off quite that easy with quantificational schemata, although, again, this isn't very bad. And we have to employ a technique known as expansion. And so what I'm going to do in a moment is I'm going to show you some very simple expansions in very small universes of discourse. And so a universe of discourse all that means is it's a specification of the objects we're talking about. With our quantificational schemata. Okay. And to give you an example of why we might want to specify universe of discourse, right? Um, so, suppose that I say, right, I send out an email at the end of the class, PX for X passed the class. Right, and I say, everyone passed the class. Right? That would be great. I hope you all do pass. I'm not being facetious there. I really hope you all do. So, and we wanted to think about, well, is this true or false? Well, if I mean everyone, like everyone in the world that ever has existed or will exist, then obviously it's false because, most people alive have never taken and will never take a logic course, for better or for worse. So that would be false, kind of in an unrestricted universe of discourse. But if I was like, universe of discourse, students in the class. Also, I suppose that I didn't pass this class. I passed another class that covered the same. Anyway. So, and to represent a universe of discourse, one of the conventions that we can adopt is we can just write UD colon and then our universe of discourse. So if we restrict our universe of discourse to students in the class, and I say, if you all get A's or whatever, I send out an email, everyone passed the class, then I've said something true. So that's all the UD is. Now for expansions, something that I'm going to do here is I'm just going, because for expansions, we're going to want a very, very small universe of discourse. So they're frequently going to be something like just A or B, A or B or C. And what that means is that when we're doing expansions, we don't really care about the specific details. We just want to use these to reason about what quantifiers mean. And so what this means, if you ever just see like an A, a B, or a C, this is a 3-element universe. And we could stipulate these letters to stand for something, but for the purposes of this, the semantics, doesn't really matter what they stand for. So we're just going to say it's a 3-element universe. A is the first element, B is the second element, C is the third element. Okay. So what I'm going to do is I'm just going to do the expansions and then explain what I did. You will have to do some of these, but they will not be very difficult. They won't be any harder than what I'm giving you. I won't stack quantifiers. Depending how tired I'm feeling in 15 minutes, I might show you an example with stack quantifiers, but I'm not going to make you do expansions. So consider the schema, this schema. Right? Every X is such that if it's an F, then it's a G, or all Fs are Gs, or there are a bunch of different ways that we could translate that. So what we do is, 3 elements in our universe, A, B, and C. Right? I'm going to use this to illustrate what the technical meaning of this quantifier is. So what we do is... So in a universe of only 3 elements, we do not need quantifiers. We do not need quantifiers because, there are only 3 elements. If we say all Fs are Gs and there are 3 things, or for every X, if it's an F, then it's a G, and there are 3 things in the universe, what that means is... this. right? So in a 3-element universe, the expression every x is such that if it's an x, if it's an f, then it's a g, means that if A is an F, then it's a G, and if B is an F, then it's a G, and if C is an F, then it's a G, right? So that's what our quantifier means. You know, if we had a 4-element universe, you know, and so on and so forth. And it's important to note here that the universal quantifier, we need to connect these instances with conjunctions, right? Because again, if we say that all f's are g's, or for every x, if it's an f, then it's a g, what we mean is that if A is an f, then it's a g, and if B is an f, then it's a g, and if C is an f, then it's a g, and if D is an f, then it's a g. Right, but let's keep it to 3 for right now. Okay, and so that's how we reason about what the universal quantifier means. You know, if we had the schema, right, we wanted to expand this in the same universe, it'd just be FA and FB and FC. Right, you know, if we have this schema, and we wanted to expand it in a 3-element universe. Oh, wait, I screwed that up. Getting ahead of myself. They have to be bound variables. Right, this is just, you know, or let's expand this in a 2-element universe. So just A and B, this would be and right, yeah. So what we did to do this was the steps for doing an expansion, I guess. I'm not going to write them down because I think this is pretty easy, at least when you don't have stat quantifiers, is so we look at our schema, right? We note the bound variables, and we look at our universe of discourse, right? And so what we do is we first, like here, we drop all of the bound variables to the first element in our universe of discourse. Then we drop all of the bound variables to the second element in our universe of discourse, and then we connect them with a conjunction. Now, if we had something like this, right, I don't know, everything sucks and Trump is orange. That's one possible translation of this, right? How this would work in our universe of discourse is 2 elements again, to save me some writing, right? So we don't do anything to free variables like t, right? So this would expand into, oh, actually, conjunction might confuse you. I'm going to change this to an or. Sorry about that. Right, so the only tricky thing is if you have a free variable, you don't do anything to that. That has to stay the way it is. This only affects, the expansion only affects the bound variables. And if we had an existentially quantified schema, such as let's make this 3 elements again. So this same basic process, except we connect the schema that we get by dropping the bound variables for elements with alternation. And so what that looks like is right. Same exact process. We look at our schema, we look at the bound variables, then we drop those bound variables to the first element in our universe of discourse. Then we drop them to the second element in our universe of discourse. Then we drop them to the third element in our universe of discourse, and so on and so forth. And the only difference between this and what we did with the universal quantifier is we connect these dropped, technically they're instances, I guess, of, that's what we call them. That'll become important in a few chapters, but it isn't right now, so don't worry about it. We connect our instances that we got by dropping the bound variable to the elements in our universe of discourse with alternations, ors instead of ands, right? And that should make sense. So if we remember this, what this says is, let's F for frog, G for green. If we assert the sentence in English, there exists some X such that X is a frog and X is green, or in better English, there are green frogs, and there are 3 elements in our universe of discourse, then what there are green frogs means, or some frogs are green, means that either A is a frog and A is green, or B is a frog and B is green, or C is a frog and C is green. Okay? And that's pretty much all there is to expansions. And you might be like, wow, that seems convenient. This is basically just truth functional logic. I mean, we have these B's or whatever. We could just abbreviate it away and it would look like a Boolean term schema. And you might be like, so why do we need these stupid quantifier things? And the answer is, if you have something like UD, the actual universe, and if you wanted to say like all pizzas are delicious, right? And if we didn't have quantifiers, you'd have to come up with a list of every object that exists in the actual universe. And you'd start with like PA, therefore GA, and PB, therefore DB, and so on. But one, we don't know how many objects exist in the universe. It might be an infinite number of objects. In mathematics, and we can quantify over mathematical expressions, as you'll see in a chapter or two, it can be very useful to quantify over mathematical expressions. There are actual infinities, so we couldn't do this even in principle, right? And so unfortunately, we actually do need our quantifiers. We can't just get rid of them with expansions. But I think that's it. Is that it? Yeah, that's it. That's all there is to this video. I know this was kind of a lot conceptually, but you don't have to do that much new stuff, so hopefully it's not too bad. And yeah, I hope that all made sense and was reasonably coherent. Try the exercises. Good luck on your learning practice, and I will see y'all probably never. I never see y'all. I will be back here talking to you in a week. Bye.